Greetings, guys. Here is our first lesson called parent functions. Parent functions, well, every graph out there has its most stripped down, simplest form. So the ones I have right here, let me show you the whole thing. We're going to start with these 6 because we have to start somewhere. Anyway, the first one you should recognize, that's the parabola. The second one to the right there, that's the absolute value graph. Then I have a root graph, a third power, and then down at the bottom I have something called rational graphs, and I hear a trash truck in the background. Please ignore that. Anyway, here we go. You guys know, and I'm going to start over here, that parabolic functions can go anywhere on this graph. They could be over here. They could be over here. They could be upside down. They could do all kinds of stuff. A parabolic graph has that eurific shape to it. Now I'm going to get rid of those. But what all graphs have in common is a method for motion. So let's suppose instead of y equals x squared, they gave me something like y equals x plus 2 squared minus 3. What if they gave me that instead? Please ignore the trash truck. Well, here's how all graphs move. Whatever's in parentheses, it's an opposite motion. It's true for all functions. I don't have time to go into it in depth, but as we progress through the class, you'll notice this. So technically what you're doing is you're mentally setting this piece of the puzzle equal to 0 in your head. So I'd have to plug in -2 to make that chunk equal 0. What I am doing, since it's a parabola, we actually have a name for this. We say, oh, -2, that's the x-coordinate of my vertex. And then what about this dude over here? Well, this guy is the y motion. So whenever we're sketching a graph, and I use the word sketch, sketching a graph means you're trying to make just a rough sketch of it. You're not plugging in points. It's not you're making a table of values. You're not going to get exactly precise. You want to have an estimate of where that graph is and what ground it's covering. So let's go back up here. I have a coordinate system. So here's how you're going to do the assignment. For example, let's say this was question 1. I want you to sketch this parabola. So you're going to go left 2 units. You're going to go down 3 units. And hopefully you remember this from Algebra 1. There's no negative value here. There's no negative there. So I'm going to get rid of it. There's no negative there. If there was, this graph would open downward. But it doesn't. So this right here is where my vertex is. And that parabola will open upward. And I am going to sketch this graph to the best of my ability. Now, should it be perfectly symmetric on both sides? Yes, but I'm just making a rough sketch. I'm going to try and do it the best I can, trash truck. But there we go. We have what's called a parabolic graph graphed using its function or its rules of motion that all functions follow. So, we'll do a quick one down here. But let me write this out. I'm going to give a coordinate system. And let's suppose they want me to sketch y equals negative quantity squared. This time I'm going to say -1. And then let's say something like +4. So here's all I need you to do to get this assignment rolling, this very first assignment. Obey the rules of motion. This is a parabolic function because it's squared. This guy is going to go up, down, right, or left 1 unit. It's going to go whatever the opposite of that is. Remember, you're setting that parenthesis equal to 0 in your head, so x would have to be equal to 1. This is my up-down motion over here, so it's like that. This would be considered my vertex, since I'm graphing a parabolic function, but I don't want to get married to the name vertex, because the other shapes that I'm going to have you move around, they don't have vertices. See this guy right here? He doesn't have a vertice. This guy right, that's a vertex. What crazy. But he will obey the exact same rules of motion that this parabola does. So here we go. I'm going to go 1 to the right. I'm going to go up 4. Boom. This graph opens downward. So I'm going to go like this. And you might say, well, how do you know that's where it crosses the y? How do you know exactly where it crosses the x? You don't. We're making a rough sketch. We just want to have a ballpark idea. Where does this graph live? Now, here's the thing with this, guys. I want you to get used to this. In case the internet ever goes down or Canvas goes down, I don't know, I always put the assignments in my videos. So this sheet right here, this parent function sheet, you need to memorize what these 6 graphs look like. We will revisit them as we go through the school year. There's 6 graphs there. Know what they look like. So like for y equals x to the 3rd here, see this guy? It's a twist. It looks like a little twisting motion there. That's what it looks like. I'm going to undo that. There we go. But this sheet here, this parent function sheet, I will include this on Canvas. But in case Canvas goes down, here you have it. It's going to be embedded in this video forever. Then, just so you know, I'm getting to it. Whoops, I'm getting to this. Here's the assignment you're going to find on Canvas. It says, sketch these parent functions and tell me their domains and ranges. We still have to get through all that, but here you go. Here is the assignment that I want you to practice. This would be called assignment 1. So, let's get back to it. And by the way, you can always pause stuff since it's a video. You can take a picture of it, then you have it with you. But let's go back up. So this guy, this parabolic function, well, guess what? I'm going to do this one right next to it. I'm going to do this guy right next to it. Y equals, so here's another example. Y equals absolute value of x minus 4 plus 2. Hey, this is not a parabola. This is an absolute value function. No biggie. It follows the same rules of motion. I am going to go down. Come on. Yeah. And then across. Yay. Hey, set it equal to 0 in your mind. What? Take away 4 would give you 0? 4. So that means 1, 2, 3, 4 units to the right. This is always determining sideways motion. This is always going to be your up or down. So I'm going to go up 2. So you'll hear me say this a lot. Whatever's here, you're going to do the opposite of. Whatever's here, you're going to do the same. Opposite, same. So here we go. I went 4 to the right. I went up 2. And I go, what does an absolute value graph look like? Well, I have this already memorized. So I just say it's V-licious. Look at that. Beautiful. Cool. It's a rough sketch. Doesn't have to be exactly perfect. That's not the point of today's lesson. Now let's talk about domain and range. Because domain and range, there's different ways to do it. We are going to use something called interval notation, because we use this a lot in calculus, so I want you to be familiar with it. Here is the deal with this. Interval notation, it mimics the concept of a number line. And when you sketch a graph, guess what? You have an x-axis, which is a horizontal number line, and you have a y-axis, and that's a vertical number line. So, domain. This is how we do this. We don't want to write out the whole word domain. That's busy work. So in math, we have shortcuts for everything. So we say domain. Well, what's the domain? How far, and I'm going to change colors here. How far does this graph go to the left? How far does this graph go to the right? Now think about it. A parabolic function, well, it goes down, but as it's going downward, it's constantly going outward forever. So we say this thing is infinitely going to the left. We call it negative infinity. And on the right-hand side over here, as it's going downward, oh my God, my hand, it's also going outward. So we'd say this thing goes to the right forever. Now look at how I wrote that. Here's how I'm going to fill in the blanks here. When you use interval notation, you're either using parentheses or brackets. You'll see a bracket in a second. So I put a comma between it. That answer is completed. You might look at that and say, what? But let me go through a couple and then you'll go, oh, this is easy. So interval notation, the domain means sideways motion, sideways. It goes to the left forever, it goes to the right forever. But it's going down. Doesn't matter. Domain only cares about sideways activity, doesn't care about up or down. So let's talk about range. So if I want to find the range of this function, you guessed it, I'm going to just be discussing y activity. Not x activity, just y activity. So I'm going to do this one in green. What the heck? Let's do green. And here's how this one's going to work. We always go from lowest value to highest value. The lowest value is always on the left. The highest value is always on the right. So do you see how this graph is going down forever? Remember, range doesn't care about sideways. Range just cares about up and down. So this thing is going down forever, down forever. I'm going to put a bracket, or sorry, a parenthesis, and say negative infinity. That's telling somebody this graph goes down forever. But as you can see, this graph has a top to it. It stops right there at 4. That's where it stops. Now, 4 is an actual number. I can have and hold. I can put in my pocket 4. See, infinity is not a number, it's a concept. I can't give you infinity dollars, whoops, or anything like that. So here we go. We use a bracket when it's an actual achievable value. Now remember, the beauty of any online lesson is you can watch it as many times as you need to. You can pause it whenever you need to. But all I'm trying to show you guys today is how to sketch a parent function and then tell me its domain and range. So I'm going to go back. Let's do this. We're going to go black pen. Come on. There we go. And we're going to do the domain and the range for this function that we just did, this absolute value guy. So here we go. I'm going to use red for domain again. And I'm going to say, you know what? This function, as it goes up, it's also going outward forever. As it goes up on this side, it's going outward forever. That's what the little arrows on a graph indicate. It means forever. It's going infinitely that direction. So on the domain, I would say, hey, you know what? The domain would be, it goes to the left forever, it goes to the right forever, it does not stop. That's why I wanted to pair up parabolic functions with absolute value functions, because they have very similar domain and range concepts. Now, take a look at it. Let's go back. We're going to get a green pen, and we're going to do the range. It appears to me that this graph has a lowest value at 2, and then it goes upward. See, range only cares about down or up. So here we go. 2 is an achievable number. 2, it's right there. 2 is not an... So I use a bracket. Long story short. And I put a 2, then I put a comma, and then I say this thing goes upward forever, so I put an infinity. And that is the correct domain and range for this example, for this for this absolute value function. So here, let's go down a little bit. So like number 1 here, see this? you would say I go left 1, down 4. And then you would sketch a graph. Would that graph open upward or downward? I'd say up, because there's no negative right there. I'm going to get rid of that negative because that's not on there. I'm also going to get rid of that check mark because I want to keep this clean. So anyway, how about number 2 over here? Number 2, well, that's going to go opposite, same. So it's going to go left 3 and down 4. If I go left 3, down 4, I can put a dot there. I can sketch an absolute value graph, and then I could tell you its domain and range using interval notation. Now, before I go on, because I want to make sure I make this, I'm trying not to make my lessons take forever to get the point across, because you can always clarify stuff and ask me questions when we Zoom. So here we go. Let's take a look at, wait, let me get a black pen. Let's take a look at this guy. I'm going to jump over to x to the 3rd, but I'm going to do x minus 4 to the 3rd. So this is the cube function. This is the one that twists. Hey, where's the other part? Well, I didn't write one in, but if it makes your brain happy, you could say plus 0. You could do that if that makes your brain happy. So what's going to happen here is opposite, same. When I sketch this graph, it's going to go, come on, 1, 2, 3, 4 units to the right. It won't go up or down, so there's a dot right there. And then I go, what does the 3rd power graph look like? It's the twist. It looks like this. It goes, whoosh. That's a rough sketch. That is it. That's it. You're done. Now, the nice thing about any cubic, I'm just going to jump right into it. Domain. Well, let me go down a little. Domain, negative infinity to infinity. Range, negative infinity to infinity. I don't even have to think about this one. No matter what you do to a 3rd power graph, it will always go outward as it goes upward. It will also go outward as it goes downward. So my domain, always negative infinity to infinity. If I wanted to do the range, it's going to go up forever. It's going to go down forever. That's how you say up and down forever. But please notice this on interval notation. You will always have the lowest stuff over here, the highest stuff over here. Negative infinity on the left, positive infinity on the right. Negative infinity is the left, positive infinity is on the right. Always. You go from low to high. When you do interval notation, you are mimicking the concept of a number line. So you go from lowest to highest. All right, let's go and look at what a flipped one of these looks like. So I'm going to do this. Y equals negative x third plus 2. Hey, you left out one of the moves. Yeah, that's what makes it a little more difficult when I leave something out. So this guy could be rewritten. I could rewrite this, if it helps my brain, as negative x plus nothing to the 3rd power plus 2. I could write it like that if I wanted. Surely could. That means I'm not going sideways, but I'm going to just go up 2. Opposite. Well, the opposite of nothing is nothing. Oh my God, trash truck. Same. Boom. Now here's the thing. A twist, when a graph is a twist, I call it a twist. It's 3rd power. When it's a twist and you flip it. What? Flip it. Yeah, when you put a negative on something, you are inverting it. You're flipping it over. That means what's up is down and what's down is up. When it comes to flipping a 3rd power function, some people have trouble visualizing it. So I'm going to do it this way. I'm going to say what is up would be Oh, crud, I didn't want that to happen. Hang on. What's up would be down. What's down would be up. That would be the correct version of that graph. Now, of course, you don't want this guy here because he's not the picture I'm looking at. That's the graph I want to see because that would be a flipped cubic graph. Now, I also did something a little sloppy here, but that's because I'm using an electronic pen and I'm not really, this is not my normal work a day. Anyway, this almost looks like it's going to go vertical, but it's not. It's as it goes down, it will go out forever. It will. As it goes up, it will go out forever. So I'm telling you, ain't no lie. It's always going to be this for a third power graph when you're doing domains and ranges. You cannot graph this function without that happening, even though it's been flipped. So one strategy that makes it easier to draw a flipped third power graph is draw it in two pieces, right? So here, I'm going to do this. So let's suppose I got a graph over here, but it's been flipped, right? So let's suppose that's the middle of what the heck, Draw one part, then draw the other part. Pick up your pencil if you have to make it work. Sometimes people find that easier. Now let's look. If you look at the assignment that we have coming, problem number 12 appears to be a flipped third power problem. Oh, yes, it does. How about number 11? Is it flipped or not? No, it's not. But we have some square root functions to graph, and we have some rational functions to graph. So let's finish this up. Hopefully in 10 minutes here, I'm hoping, guys. Let's do it. I'm going to scroll down, and let's take a look at what a square root function would look like. So I'm going to start here. Y equals, let's do the square root of x minus 3 plus 1. Okay, what is this guy going to look like? Well, if you look at the parent function sheet, which hopefully by now you already took a picture of it and you just have it on your phone so you can scroll through that and look at it. That's what my kids would do. Here we go. I'm going to draw, come on, coordinate system, yeah. Come on. There it is. Opposite, same. I'm going to speed things up. Opposite is sideways motion. Same is vertical motion. I have a starting point now because my parent function looks like this. That's what it looks like. That's what my parent looks like. You don't believe me? Scroll up to the top. Oh, wait, you can't scroll. But you could have taken a picture. Anyway, that's what that guy's going to look like. He doesn't start at the origin like the original. He's been moved. But let's talk about the domain on this one. Okay, so once again, I'm going to do domain. I'm going to do range. So let's do domain in red. I'm just trying to color code it, make it easier on you. Do you guys see that this guy right here is a beginning location? That beginning location is part of my graph. That's why it gets a bracket. And X motion. Domain is X motion. Everything that goes this way. So it starts at 3 and it gets infinitely big going that way. That's the domain. I'm showing you how to write things in interval notation. Now, let's talk about range. I'm going to use green. Range, hey, it starts here, but it goes this way. When you talk about range, you're going up. So when I say it starts there, and I'm going to get rid of that so you don't think that, okay, so it started at y equals 1, and it went upward. So that would be the correct domain and range. And this makes me think about Christmas. I don't know, red and green. Now, here we go, y equals. How about we do a negative root x minus, or now we'll do plus because we did minus on the last one. We'll do that. Whoa. You know what? Yeah. Come on. There you go. And there you go. All right. I took away one of the moves, but you could write a +0 if that makes your brain happier. You could. So now I have opposite. Same. So I go left 4, I don't go up or down. Same motion as a parabola, we just don't call it a vertex. Now, here's the thing. This guy right here is what the normal dude would look like. But we have negated it. So it's going to flip. It's going to flip. So instead of going up, it's going to go down. I'm going to do it in blue so you can compare the two. That's this graph. That's this guy. The black graph would be if I took away the minus. If I took that minus away, the black graph is perfect. But since it's been negated, it's the blue graph. It gets reflected over the x, they call that. I just call it flipping. It flipped. So here we go. Let's talk about domain and range. Oh, wait. I'm trying to stay color-coded the way. Okay. Domain. Range. So here we go. Let's go red and green. Domain. Hopefully you figured out that that is the x value that it starts at. So it starts at -4. And yes, -4 is a number it achieves. It is. And then it goes all the way to the right forever. It never stops. Bam. So we do that. Notice whenever I write infinity, I never put a bracket on it. Mom always said, never put a bracket on infinity. It's true. That's why she said that all those years. Now, let's do the range. Range is going to mess you up. So let me do it wrong the first time, explain why it's wrong. So here's the wrong way to do this. And a lot of people do this. That's why I'm going to say it. They go, hey, this thing's going down. But the highest value it hits is right on the x-axis, so it's 0. So it goes 0 to -infinity because it's going down. And this is incorrect. Please don't do this. Whenever you write domains or ranges, you are mimicking the concept of a number line. Number lines don't start at 0 and then go to the right and become negative. So here's the easy way to remember this. -infinity. If you ever have -infinity in your answer, it's on the left. Here's the correct answer. It's very close. But you have to obey the rules that were set up by all the math geeks that came before ye. So here we go. Range, -infinity to 0. That's that guy. Notice this graph, a parabolic graph. If I were to do this, it would continue upward and outward forever. It would. It does climb. All right? It just doesn't go very fast. The same thing goes with this. If it's going to drop, it's going to continue to drop. It just won't drop really fast, but it will drop forever. Forever it goes downward. So here's the thing. Make sure, never do this. If you have a -infinity as part of your answer, it will always be on the left side in your interval notation. All right, we got 2 more to hit, and then you're going to sketch some graphs. So I'm going to pretend I'm you a little bit here, and I'm going to scroll down so I have a clean sheet to start with, and I'm going to talk about these guys. Let's do 1 over x plus 2 minus 3. Now, this is called a rational function. You will see these a lot in calculus. So these guys, same deal. Hey, left, opposite, same. So I'm going to go left 2, down 3. But when I go left 2, down 3, here's what happens with this thing. Come on. There we go. Tighten up. Left 2, down 3. 1, 2, 3. There's dot. Okay. That dot is kind of like my new origin for this graph. I went left 2, down 3. Check this out. This guy right here is a boundary marker for this graph. It's called an asymptote. This guy is called a boundary marker for this graph. It is called an asymptote. An asymptote is a boundary in a graph. Now, what do you mean? Why? What? Hey, let's just get the sketching. Today, all you need to know how to do is sketch things correctly and tell me their domain and range. That's it. But I wanted you to see that there are graphs out there that have asymptotic behavior. A rational function is something we have to talk about. Rational function is one with variables in the bottom. Or it could have variables in the top and the bottom. We're just not going to go there today. Remember, we're focusing just on these parent functions. So here we go. If you look at the parent function, I'm just going to scroll up real quick. Hope it doesn't mess me up. If you look at the parent function for this guy, it's this one right here. It's this dude, 1 over x. So you'll see I put little dashes here. Whoops, oh my gosh, that's bad. For the asymptotes, because this graph has not been shifted up, down, right, or left at all, this guy. So let's go back down. Here we go. And I'm going to sketch this graph. It's going to go like this. Swoop and swoop. So this rational function here is made up of two congruent curves. They look the same. These curves look identical to each other. I'm trying my best to draw them that way, but once again, this is just a rough sketch. It's not going to be perfect unless I need to make it perfect. That's not happening today. This is a rough sketch. But all rational functions will obey the same exact rules of motion as everything else. The only difference, it has asymptotes. And if it has asymptotes, it means boundary lines that the function will try to approach but never get there. So they're like border lines. Or I like to think of this as barbed wire. You don't want to touch barbed wire. You do not want to crush through barbed wire, but you can get close to it. Anyway, let's talk about domain and range here. So here's the thing. I'm going to use my colors, and I'm going to re-sketch this graph. So I'm going to say, let's talk about domain. Do you guys agree with me that this graph with this arrow on the end means it's going to go to the left forever? Yes, it is. It's going to go to the left forever. If I sketch this graph in red here, do you agree with me that it is going to go to the right forever? That's what the arrow indicates, and I say yes. The problem is there is a break in the middle, okay? So here's the rule for this. When you have asymptotic functions, you will never use brackets. Mom always said, no brackets on asymptotic functions. What does that mean? It means we have a break in the action at -2 here. We have a break in the action. So when I write the domain for an asymptotic function, I tell people, hey, it goes to the left forever, but it hits -2 in this case. It hits -2 and there is a break in the break in the action. Then it picks up on the other side of -2 and it goes infinitely big. This symbol in mathematics means unified. So all the information on this side of the asymptote unified with all the information on this side of the asymptote. Let's talk about range, because range is going to be strange. That's a fresh rhyme. Do you agree with me when I draw this picture? It goes down forever. It's going down forever. It surely is. When I draw this picture, arrows indicate that the graph is going up forever. But when I draw this picture, you'll notice there is a boundary marker. There's that barbed wire right down the middle there. Where does that boundary exist? It exists at -3. So when I write the range for this, I would tell somebody it goes down forever. But when you get to -3, boom, there is a break in the action. And then it picks up on the other side of -3 and goes up forever. This is why I wanted to introduce to you guys this interval notation so that you're used to reading it. It's not difficult. Don't let it be hard. But that's how you indicate to somebody that everything on the left side of -3 sorry, on the bottom side of -3, and everything that's on the top side of -3, and you don't use brackets at all to indicate that there is a boundary marker there. Whenever you use a bracket, it's an achievable value. So look, see how this guy had an achievable value, bracket, bracket. This guy, achievable value, bracket, bracket. This guy, no brackets on asymptotic functions, ever. All right, let's take a look at one more, and then we're going to call it a day, and you're going to try and practice. So here's you. You open up the worksheet, and you say, I got to sketch some of these graphs. This is the question that he wants me to work on right here. And I'm going to sketch this graph. So I say, okay, this is the one on the parent function sheet that looks like this. And you'll notice on my parent function sheet, it looks like this. And I got this dude, the Atari symbol, if you play video games like Pong. Yeah, I'm that old. Okay, it's supposed to be symmetric on both sides, but I'm making a real quick sketch. So here we go. I'm going to sketch this graph. Come on, tighten up. There you go. There you go. All right. Guess what? I didn't move sideways at all. Opposite, same. I didn't move sideways at all. If it makes your brain happier, you're always welcome to say this. Okay, so what's happening in this case? Well, it appears I'm going to flip this graph over. I am going to flip this guy. But I have to do my rules of motion first. So I'm not going sideways. I am not going to go sideways. That means my asymptote will be right down the middle. I'm not going sideways. But I am going to go up 3 units. 1, 2, 3. Which means I'm going to have an asymptote right there. So there's my 2 asymptotes. Now, normally I would do this. I would have this graph go up. I'm going to get rid of those because that's not what's going to happen here. I'm going to flip this graph. I'm flipping this graph so everything's going to go down now. So this is, trying to make it look symmetric. That's not looking very symmetric, but you know what? I'm not going to punish you either for that. It's a rough sketch. We're just practicing sketching graphs following the rules of motion. All righty. Let's see. Do you guys see, like I do, that this thing's going to the left forever and to the right forever? I hope you do see that. And remember, sideways motion, that's domain. So I'm going to say the domain for this guy, it goes to the left forever. Then there's a location where there's an asymptote, and then we unify it with that same number, and then it goes to the right forever. Now, I did that on purpose so you can see there's a pattern here. Every single time you do domains and ranges for rational stuff, well, on this one, what's that question mark? What's that number that I left out? Well, when you draw this graph, where would you have to pick up your pen? You'd have to pick it up at 0. So let's fill in the correct response here. These should both be, whoop, I need a pen, zeros. Now, let's do the range, and don't be fooled, because this is where people make mistakes. They go, oh, I'll just do this. La, 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 he told me. La, 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 I could do this. This function is 1 over x squared. Not all rational functions have this and this at the same time. This guy right here, I'm going to erase, because I don't need any of this stuff. I do need to fill in this blank, and I'm going to fill that blank in with the number 3. Because take a look at this picture. The picture states that it goes downward forever. It does. It goes downward forever. But it has a ceiling. It gets blocked off right here. Bam! You can't break through this barrier. So what do? You tell somebody there's a barrier at 3. How do they know it's a barrier? Because you didn't use a bracket. Okay, that is a huge, huge lesson. It is. That's a lot of information. But once again, what are you going to do? Let's scroll up here. I'm going to look up and say, here's the questions I want you guys to try. This is our very first assignment. I want you to hey, I'm going to sketch this picture. Well, that one's a parabola. Then you tell me its domain and range. I'm going to sketch this picture. That's an absolute value. You're going to tell me its domain and range, etc., etc., etc. And then we'll take it from there. But I want you to know that every function, no matter what it is, and we're going to see a lot of them, has a simplest format. So like a parabola, that's its simplest format. An absolute value, simplest format. Third power, simplest format, etc., etc. Everybody here has a simplest format. But every single one of these guys will move just like that parabola used to move when we were in Algebra 1. Okay, that is the end of this lesson. Please do the practice problems, sketch the graph, domain and range. Use interval notation. I'll see you guys on the other side. Bye-bye.